So what is this? Is this a drilling process or screwing process or whatever? It's some kind of interesting animation. So this video will be talking about how can we produce such animation and whatsoever. Hello guys, my name is Tu. So for this video, I'll be talking about how can we produce some of the interesting animation that has been shown previously. So without further ado, let's go ahead and click on new buttons. Now we're going to create from scratch the 3D model for the geometry. So let's begin with creating a cylinder with a diameter of 10 millimeters and height of 100 millimeters and OK. Then we'll just quickly do Control T command to duplicate this geometry. Simply put it over here, the handle. Just create a duplicate copies and just offset the distance of -100. So I'm trying to move it down. Sorry. Turn off the move handle only and try to do it again. And give it some space in between, probably 10 millimeters gap, and OK. Then, so yeah, we are ready with the 3D geometry. Now let's go ahead to the Simcenter application. So first of all, click on New, the File tabs, and go ahead to Pre-Post application. Now let's create a new FEM and simulation files. We'll be using all the visible geometries as shown. Since we are not talking about the meshing, so we're just going to quickly skip the mesh. But we are more interested on talking about the new solution, which is solution 402 Multistep Nonlinear Kinematics, which allows us to produce the kinematics animation previously. So let's quickly put some meaningful names such as 402, then OK. Now we'll just we'll be using the nonlinear dynamics subcase because because when it involves very significant displacement or rotations, therefore it is recommended to use nonlinear dynamics. So we'll just click OK for now and proceed with the automatic meshing for this two geometry. Just pick these two and automatic size per body and click OK. So we are going to quickly create the 1D connections. So from here, I'll be using this, I'll be quickly creating probably a point. So let's create a point here between these two surfaces. So between 2 points, point here and second point here. So that will be here. Okay. Let's create a 1D connection, which is pointer face, selecting this point here and select this face here, apply as a RBE2, and we're going to do the same for this face. So from this point to this face, and OK. So I'm just going to quickly check how many nodes it is available at the middle here. I'll need to make sure that there are 2 nodes because I want to separate these 2 mesh. So because there are only currently 1 node, 3199, so I'll need to detach this node. So to detach it, you can go to the Nodes and Elements tab, choose Detach this element, and deselect all the nodes except for this this node at the middle. Click OK, and now let's quickly check again the nodes quantity. So currently there are 2 nodes, so this is as expected. Now let's create the CJoint. Let's create some gap in between. So for that, let's use the translate. We just quickly translate one of the nodes and bring it in the positive Z direction in order to create a gap. So let's create apply. Oh, sorry. So this is overlapping. Then probably I just quickly select the same node and let it go in the opposite direction as such. So now that it has a 1 millimeter gap, let's create the joints in between, which is by using the 1D connections, node to node, and we'll be using CJoint. So CJoint here. So CJoint is a new element which is available in solution 402. So 402 is also considered as a new solver from LMS Simcenter. So let's quickly select this node as the source and this node as the target, and click OK. So by doing so, we have a 1D elements in between here. So let's look into the PJoint property. So let's go to double click on CJoint, PJoints, and click on the edit button. Notice that currently the user interface for NX does not support the screw type, but in fact, Simcenter Nastran does support screw animation. Therefore, from what you see in the previous animation, so anyway, these are some of the out of the box type, revolute joints type, inline, and others. So just to show you the library, the dictionary, the so-called dictionary for Nastran. So let's find PJoint. So this is the keyword information for kinematic joint properties for solution 402. So this is the keyword PJoint, and PID refers to the identification ID, the number for this PJoint, which is usually we'll just keep it as default. But for the type, notice that we have this screw which I'm using for my animation. Unfortunately, this keyword is not available inside the software user interface. But however, we can always add the user-defined text to override these properties and such. So for screw, if you are trying to build a screw animation, so let's look into this page here. If you're using screw, you will need to refer to the joints property such as KT, KR, and pitch. So KT is the translational stiffness, KR the rotational stiffness, and pitch refers to the screw pitch for the screw joint. So pitch means simply the translational travel distance per revolution. So these three properties are required, and these properties are located at this particular field, KT, KR, and pitch. So you need to create this user-defined text to and replace the existing data. So for that reason, I will just quickly create a dummy, dummy join, dummy information here. Then we're going to override everything at this page. For example, I'll just keep it as a slider and click OK, and OK again. So now let's proceed to defining the material properties. For example, go to this 3D collectors, P solid, and define a material, for example, steel. Okay, for example, this guy, and okay. Now, the FEM is the work on FEM level has been completed. Let's move on to the sim level. So just double click on the sim level, and we are going to define, first of all, a fixed joint. So this fixed joint will be located at this bottom here, and we need to define a kinematics driver. For example, this driver will be rotation for this P joint, even though this is remember that we have defined this as a slider, but we are going to change the PJoint property using the overriding methods later. So we'll just keep using the rotation here, for example 360 for one cycle. And we have the kinematics driver and the fixed constraint defined. Now let's try to write the input file. So we need to write the input file so that we have a reference for modification. So solve. Before I solve, I'll just quickly click on the save button, and I'll just save it at some location. Let's see, CJoint, okay, model number 2, okay, and let's write this file, solve. So we're not going to solve it, but we are going to write a reference input file. So click OK. The files are written into the local directory. So let's browse to the local directory. So browse, and the file is having an extension of .dat, which is this file. So models2 refers to the current files. So let's double click this guy, and we are going to search for PJoint. So this is the properties that we are going to overwrite. So let's just quickly copy everything, and then we just write it in the new notepad. So from here we have this information that we need to replace. For example, we are just going to keep on using the same standard field formats for small field function. Small field format for writing the syntax. That is to say, every 8 space will represent one field. For example, if I count from left to right, 1, 2, 3, 4, 5, 6, 8. This will be one field, referring to field number 1. Then again 1, 2, 3, 4, 5, 6, 7, 8 for 2, and for slider, then there will be 1, 2, 3, 4, 5, 6, 7, 8. From here, we need to replace the text. So that will be 1, 2, 3, and this is how we can write the format. So screw, yeah, sorry. Okay, and we are just going to ignore the KT and KR format, but because since we have 2 lines, we need to add a plus sign at field number 10 and field number 1 of the second row. Therefore, I'll need to quickly do some counting. So that's field number 4, 1, 2, 3, 4, 6, 7, 8. Just copy this field and paste field number 5, 6, 7, 8, 9, and the plus sign. So then add another plus sign. So that will be 1, 2, 3, 4, 5, 6, 7, and for field number 2 is empty, 3 is empty, 4, 5, 6, and 7 is the pitch. So let's put some value here, assuming that the pitch is 10 millimeters. So I'm just going to put 1, 2, 3, 4 space bar and a real number. Therefore, a real number must include the decimal point, and for example, a decimal point and a 0. And this will be how I put the user-defined text. So we are going to copy everything here and go back to Simcenter or NX application and right-click on the solution, edit, go to the bulk data, and we are going to add this text. So user-defined text, click on this button here to add the text at the end of the section. Okay. So, and before we solve, then there are some properties that we need to adjust for this solution. For example, we need to change the default parameters, strategies parameters. So let's click edit, and we need to edit this nonlinear control parameters. So for nonlinear dynamics solution, and for this reference, probably is a good idea to replace the reference force to something which is more relevant to the simulation model. For example, the weight of this geometry. So let's do a simple measurement. So we are going to measure this geometry. So it has probably this is not accurate. Let's try to do the measurement again at the CAD environment. So let's go to the go to the lowest hierarchy of the simulation file view, and from here we can try to do the measurement again. Object, solid body, this guy. So it has some weight of 0.6 Newton. So maybe we can put a more relevant reference, for example 0.6 rather than the default value. So let's go back to the sim level and right click on this subcase, edit. We're going to change this control parameters, edit the reference force from 0.001 to 0.6, and that's it. And just put some increment, for example, just 100 increment for nonlinear dynamic solution. Now let's try to solve it. But we are not going to solve directly, but we need to replace the existing PJoint property, if you still remember. So we're just using this option, right? Edit and solve input files. Okay, now let's search for the PJoint. So down. This is the property that is generated from the software. So we're just going to add a $ in front. And let's look into the user edit value. So for example, I think I missed some information. Not every information is written here. So let's add this line in as well. Okay. So let's save this file and exit. So the solver has started. So it will take some time to solve this problem. So the solution has been solved in within 1 minute plus. So let's look into the results. So just okay, and now so here are the results. Let's quickly look into the displacement. So because we have 100 steps to run 10 millimeters, so for each increment, the increment in the vertical direction is 0.1 millimeters, and the rotation is 360 degrees divided by 100, 3.6. Okay, as such. Now let's try to play the animation. So we click on the animation button, animate the iterations from start to the end, and click 0 delay and play. Okay, so this is because we did not specify the large displacement setting. So if we try to, because this is still a linear solution, so therefore rotation is not allowed, and the solution happens as such. So we also can try to add in the, so let's see, add in the large displacement. So parameters, large displacement, and OK. So we try to solve again. So just but before I solve, I'll just quickly check my user-defined text, because previously I think I have missed out some lines. So if I go and click on this button here, so I have only managed to copy one line, but actually I need to copy both lines. So I just copy this and whole content and replace here again. So OK and OK. So now let's try to solve this problem. So solve again, write, edit, and solve the input file. So search for PJoint, add the $, and scroll to the bottom. Okay, this information is here already. So let's save and run. Just exit this text file and the solving will begin. So now the solution has completed. Let's look into the results again. So let's click on the results, structural, and, displacement results, and animate, iterations, full cycle, and display. So that's it. We are getting a nice result, a nice animation of screwing or drilling animation of whatsoever. So that's it for this video. I hope you enjoyed. Thank you very much.